This next section I want to dedicate fully to one other very important concept that is at the very core of working with geometry nodes. Fields. Fields are the way to pass around and use attributes within the node tree in geometry nodes. You have already seen how important attributes are to make custom changes on a geometry, and for that we have already been using fields just without calling them as such. The fundamental idea with fields is to be able to treat attributes just the same with nodes as you do regular values. That means the ability to replace single parameters with attributes that give you individual values to each element of the geometry. That makes the entire workflow incredibly flexible, as you can build operations that are agnostic of the actual data that they are working with. Even without fully grasping how exactly fields work, they give you an intuitive workflow that is familiar from shading nodes. And once you get a real hang of them, they help you to unlock the full potential of procedural geometry operations. So, to give it a short and precise definition, fields are a way to pass around references to attributes and operations between geometry nodes. To understand what exactly that means, I have to get a little bit more into detail. Let's start with a small example to make things more tangible. If I want to displace the mesh of a plane with a noise texture, I can simply do that by plugging the color output of the noise texture into the offset input of a set position node. And if I want to modify the noise texture, I can, for example, add in an RGB curves node. And now I have control over the profile of that noise. Simple, right? This is the intuitive behavior that you would expect, having worked with Blender's shading nodes in the past. But what is actually happening here in detail is a little bit more intricate than what it looks like on the surface. So let's take a closer look at what is actually happening here. To get a noise displacement that is different for each individual vertex, we need to use a field. In the interface of the node tree, you can see two elements that identify a field. The connection link is a dashed line, and the socket is rhombus or diamond shaped. The reason that the noise texture here needs to be a field is that the offset that deforms the mesh in the set position node needs to have a different value for each point of the mesh. And this field that describes how each point gets moved depends on attributes of the geometry. And attributes give you exactly that feature where each element can have a different value. As I hover the mouse over the field socket that is used as the offset input, you can see exactly what attributes this field depends on. In this case, the field only depends on the position attribute. That is because the noise texture node, by default, uses the position attribute as a vector input as long as nothing is connected. That is also similar to the noise texture in shader nodes. For the position attribute, there also exists a field input node to use it directly in the node tree. When I connect it to the noise texture node, you can see how the result stays the same. This is essentially what the node does under the hood when no vector input is connected. And hovering over the field socket also shows the same text. Using the position field and making calculations with it also does not mean changing the actual position attribute. Fields on their own never write any actual data. They just read it and perform operations to receive data that can be used elsewhere. So similar to what I've shown earlier, how you can pass around geometry and branch it off to make duplicates, you can pass around fields to perform operations and make connections. But there's one major difference here. A field itself does not hold any actual values. The actual data of the attributes is only stored on the geometry itself. So any changes to an attribute can also only be made on the geometry it belongs to. This information is super important to understand how node trees work in geometry nodes. A field can only pass around a reference to an attribute, not the actual attribute itself. But this is very powerful. It means that I can build a field that depends on a bunch of attributes without being bound to the context of a certain geometry. So I can, for example, use the same noise texture field in combination with any other geometry. The only requirement here is that the other geometry also needs to have the attributes that the field depends on. In this case, this is not a problem. Any geometry will have the position attribute available, so this field can just be used in any geometry context, which makes this setup very flexible. So what you're really passing around with a field are instructions on how to calculate an attribute to be used in a geometry operation. In this specific case, the instructions would be something along the lines of use the position attribute to sample a noise texture, and then map the resulting values with a defined curve. The instructions given by a field like this can exist independently, isolated from any geometry. And whenever the field is used to operate on a geometry, the instructions are executed and the attributes that the field references are taken from that geometry. So just to reiterate this point because it's very important, fields only carry the instructions, not the actual data. A useful term here is the evaluation of a field. Evaluation marks the actual calculation of the values that turns the abstract concept of a field with references of attributes and field operations into actual data that can be used. And so, the evaluation of a field means the execution of the instructions, and it only happens whenever the field is being used in an operation on the geometry. There also always needs to be a geometry context to evaluate the field in. Without the context of a specific geometry, the position attribute does not make any sense as you don't have any values. In the example, this means that the field of the noise texture is evaluated for the set position node on the geometry that is passed into that node. And so, the position attribute which the field depends on is taken from that geometry, and the field is evaluated for the specific operation. That means as long as the field is passed around while it is still referencing the position attribute, the actual values on the points are not locked. They change along with the position attribute itself, until the point where they are actually evaluated. If that same field is used again later on, the context of the geometry has changed, and the position attribute is taken from that geometry that the field is evaluated on the second time. This can be quite useful to achieve certain effects, and is an inherent quality of the field system. But that also means that in some cases it can get confusing when a field's resulting values have changed between connecting it with multiple different nodes in the node tree. I will go over how to circumvent this behavior a bit later as well. This also means that I can split off a field wherever I want and add other operations on top. And the result will still be a field. I can take any diamond-shaped output of these nodes and the result is still just a field. The same is true for the inputs as well. Any input that has a diamond shape can accept a field. For example, let's add a scale node to this setup. The noise that we previously used as a vector, I connect to the scale input, and to the vector input, I connect the normal input. This way, we can basically compose a single field out of multiple other ones without any problem. You can see now that the field depends on both the normal and the position attribute, as I hover over the field socket. Other than actual attributes that are stored as data, like the position attribute for example, fields can also refer to other data that is derived from the geometry. One example would be the normal direction of the faces. This information is not stored as an attribute because it is given by the shape of the geometry implicitly. Instead, information like this should be referred to as derived data. It is derived from the geometry in general, rather than being stored on the geometry. In the case of the normal vector, it mainly depends on the position of the vertices, and so it can be calculated from that. Other examples of derived data would be, for example, the index of each element, which is just given by the order of elements in the spreadsheet editor, or other information about the geometry like the area of the faces or the angle of the edges. would be derived data. The derived data is also provided in the notary using fields, and the evaluation of derived data also happens whenever the resulting field is being used, just the same as with regular attributes. So the behavior is generally the same, and it usually isn't necessary to identify which is which. To summarize the important parts a bit, fields allow you to dynamically build operations on attributes and other geometry data to be used to manipulate geometry. The actual evaluation of a field, taking all the values of the attributes that it is referencing and calculating the result, happens only when it is used for an operation on the actual geometry. That means in practice that you can generally create fields completely disconnected from any actual geometry and then use them in the context of any geometry that provides the reference data.